Okay, let's dive into this. Have you ever stopped to wonder how the billions, and I mean literally billions, of perfectly shaped nuts and bolts holding our entire world together are actually made? And not just made, but manufactured at this incredibly massive scale with virtually zero material waste? It's one of those hidden pillars of modern engineering that we completely take for granted when we're just walking down the hardware aisle.
Well, welcome to this explainer on multi-station parts forming. Today, we're going to demystify the heavy industrial journey of turning a really simple, unassuming cylinder of wire into a highly complex engineered fastener. It's this absolutely fascinating world of immense pressure, precision timing, and robotic choreography.
So here's our roadmap for today. First, the quest for the net shape. Then we'll hit the three core forming operations. After that, we'll look at mastering the transfer mechanism, and finally, we'll pit parts formers against nut formers.
All right, kicking things off with Section 1, the quest for the net shape.
So the absolutely crucial point here is understanding the difference between what we call net shape and near net shape. In manufacturing, creating a part to its net shape means you're producing it so perfectly that it comes off the machine completely finished, maybe just minus adding a thread or doing some post-heat treating, but it needs zero secondary machining. Near net shape, on the other hand, well, that means the part still needs a little bit of secondary work, like trimming, shaving a groove, or squaring an underhead bearing surface. When parts get really highly complex, achieving that pure net shape in one single continuous process, that's the absolute pinnacle of efficiency.
And this really highlights why manufacturers absolutely love precision forging to get that net shape. It drastically minimizes post-forging costs. Because think about it, you're shaping the metal rather than cutting it away, so you use way less material, produce almost zero scrap, and use significantly less energy. It even allows for incredibly tight draft angles of just 1 to 0 degrees. Now, sure, the downside is the steep upfront cost of these highly complex multi-station machines. But when you're making millions of parts, the cost reduction from wiping out secondary machining and scrap is huge. This extreme efficiency is exactly why those fasteners you buy at the hardware store cost you pennies instead of dollars.
Which brings us right into Section 2, the three core forming operations.
So how do we actually force cold steel to literally flow like clay? Well, even though the machines we use look incredibly complex and, frankly, intimidating, they essentially perform just three fundamental processes. The whole shebang boils down to upsetting, extrusion, and trimming or piercing. Just by combining those three basic operations across multiple stations, engineers can craft some incredibly elaborate geometries.
Think about the really humble starting point of our fastener. It's just a simple cylindrical wire blank. It's literally just been drawn into the machine and cut off. But this basic, featureless slug is about to kick off a multi-station journey that will completely transform its geometry. As that blank moves to a forming station, a tool called a punch strikes it with immense force. And this is the beginning of forward extrusion. This process is used specifically to reduce the cross-section of the part. The blank is quite literally being jammed into a die.
And what's crazy is the incredible pressure actually forces the solid metal to flow in the exact same direction as the punch's motion. It forces the material to tightly fill the cavity, forming the complex stepped body of our fastener. Sometimes they do this in a closed die, but other times, if the part is super complex, they'll use something called open extrusion, where the blank isn't totally enclosed. That allows for incremental reductions across multiple stations so they don't accidentally exceed the yield strength of the metal.
Next up comes heading, which is also known as upsetting. Now, while extrusion reduces the cross-section, upsetting does the exact opposite. It increases it. The punch strikes the metal, but this time the material is gathered and flows perpendicular to the direction of the punch. So this is exactly how the wide head of a screw or a bolt is formed from that originally narrow wire. Actually, for the simplest screws out there, this might be the only forming operation they even need.
Finally, after any necessary trimming to remove excess material from the outside, or piercing to punch out material from the inside of a hollow part, boom, we achieve our perfect, fully formed net shape profile. It's totally ready to be dropped out of the machine. The transformation from a simple cut-off blank to this complex shape, all done in fractions of a second without even heating the metal, it's truly a marvel of mechanical engineering.
All right, let's keep moving to Section 3, mastering the transfer mechanism.
To do all of this in one continuous machine, taking that single blank through multiple different dies for all those extrusions and upsetting operations, we have to rely on the true unsung hero of the multi-station forming process. I love this analogy from our sources. Think of a multi-station former as an incredibly fast, highly miniaturized assembly line. Each stop along the way, each strike of the punch, is really just one incremental piece of the entire assembly process. But here's the catch, and it's a big one. On a normal automotive assembly line, the part sits on a pallet, and the pallet moves down the line, right? The part itself just stays put relative to the pallet. Well, in a multi-station header, there are no pallets. The part itself has to be individually grabbed by these robotic fingers, shuttled sideways to the exact dead center of the next die, and perfectly reoriented so it can be struck again. And it has to do this over and over, sometimes literally hundreds of times a minute, without ever dropping the part or messing up its angular orientation. Honestly, it's this incredibly complex transfer requirement that usually dictates the absolute maximum speed the machine can even run.
Finally, let's wrap up with Section 4, parts formers versus nut formers.
Okay, so we understand the forming operations and the transfer methods, but how do these massive machines actually differ based on what they're manufacturing? Well, while both types perform fundamentally the exact same upsetting, extrusion, and trimming processes using really specialized hardened tooling, the actual mechanical execution of the machine varies wildly depending on if you're making a bolt or if you're making a nut. And really, the geometry of the fastener dictates everything here. Think about it. Parts formers are designed to make screws and bolts, which are typically, long and thin. Because the part is long, the die is long. This means the internal pin that pushes the finished part out of the die, the knockout pin, has to travel a really long distance. That long stroke takes time, which means parts formers generally run a bit slower. Nut formers, on the other hand, make short, stubby, hollow parts. They require a super short stroke, which lets them run incredibly fast. Plus, bolts have a distinct head and body, so they're just transferred straight across from station to station. Nuts, however, they often need to be turned or completely flipped around by the transfer mechanism so they can be worked on from both sides.
This geometric difference also completely changes the size of the machines, because making a bolt usually just involves pretty straightforward upsetting and forward extrusion. Parts formers typically top out at about 4 stations, but nuts are surprisingly complex. They often require these tricky reverse extrusions where the material actually flows backwards over a punch, plus a final piercing operation to punch out the center hole so it can be threaded later. Because of all those extra steps, nut formers usually require 5 or even 6 separate stations just to achieve that perfect net shape.
So as we wrap up this explainer, we've seen how simple wire is transformed through extrusion and upsetting, shuttled around by insanely precise robotics to literally form the backbone of our physical world. But as engineering demands keep growing and our need to conserve materials and energy becomes even more critical, it leaves us with a really fascinating final thought. What incredibly complex shapes will the multi-station formers of tomorrow conquer without producing a single scrap of waste? Thank you so much for joining me on this explainer, and keep questioning how the world around you is built.